Okay, so welcome everyone to this presentation, which will be about automated security with a foundation model. And in particular, the question that I will try to answer throughout this presentation is what role will foundation models play in the next generation of security systems? So how will they be used in incident response, in threat hunting, in vulnerability analysis, and more broadly, how will they be used in security operations? So a foundation model in this context could be, for example, a large language model, or it could be a time series model, or a multimodal model, depending on the particular use case. And maybe I'm optimistic, but my view is that these models will be very useful in cybersecurity. And in particular, I think that they can enable this long-standing goal of autonomous security systems. So security systems with a very high level of automation that can automatically adapt to a changing environment. Now, before I explain in detail why I think that is the case, let me start out by just reviewing the current state of the art when it comes to autonomous security, which can be understood on a high level through the following picture. So the starting point here is that we have a target system. And this could be, for example, an IT system or a cyber physical system. And that's where we want to automate the security operations. So the first step of this methodology is that we take the configuration of the target system and we emulate it to create a so-called digital twin, namely a virtual replica of the target system that runs the same software and the same configuration, but on virtualized hardware. And this twin then provides us with a safe environment where we can run experiments and we can collect a lot of measurement data. That data can then be used to identify a mathematical model of the system. For example, a Markov decision process or a game. And given that model, we can then apply numerical methods to compute an optimal or a near optimal security strategy automatically. For example, reinforcement learning or dynamic programming. We can then take that strategy, extract it from the simulation, and evaluate it on the digital twin. And if that evaluation is deemed successful, we may also deploy it on the target system. And this whole cycle can, of course, be repeated many times in an online learning fashion. Now, from a practical point of view, we know that this methodology works. So we have numerous empirical proofs by now to support that claim. However, it is currently limited to relatively small-scale systems. And the reason for that is that for this methodology to be effective, we require that a simulation captures all of the relevant attack scenarios that can occur on the target system. And if you have a very large target system, there's going to be thousands of such scenarios. So you will need an enormous amount of data in order to identify a simulation that captures all of those scenarios. And that becomes a big bottleneck in practice. And this is precisely where I think that foundation models can be very useful. So instead of trying to collect all of this data from scratch and creating the simulation, we can sort of bootstrap our simulation from the knowledge that is already encoded in the foundation model. And the rest of this talk will be about a framework that we have developed for doing precisely this. So I will start by giving a high-level overview of the framework and motivating it and focusing on the architecture. Then I will present our main theoretical results, which is mostly about reliability. So how can we build a reliable security system from an unreliable foundation model? And then I will present a experimental validation of our framework on an incident response use case, where I will compare it to the state of the art. And also, if you have time in the end, I may do a live demonstration. So from a architectural point of view, our framework can be understood through the following pipeline. Now, there is quite a lot going on in this figure, so let me walk you through it. The starting point is that we view the foundation model essentially as a control policy. So we can prompt the model with details about the task that we're trying to solve, security task, and then we can instruct it to generate an action for completing the task. Now, if we query the model many times with the same input, we may get slightly different answers every time. So essentially, it is a stochastic control policy that gives us a posterior distribution over potential actions. And just like we can use the model to generate an action, we can also use it to predict the outcome of an action. And in our framework, we use such look-ahead predictions to evaluate different actions and to measure their consistency. So if all of the predictions are very similar, we say that the model is consistent, and in that case, we simply pick the action that, according to our predictions, leads to the best outcome. However, if the predictions contradict each other and are very different, then we say that the model is inconsistent, and we then refine the actions through in-context learning from feedback. And this feedback can be collected in many ways. It can, for example, be that we ask a security expert or that we collect feedback from a digital twin. And by having this loop with verification and then refinement, we can actually provide quite strong theoretical guarantees of this framework. But before I go into details about our theoretical results, let me start by just walking through the steps here and go explaining a little bit more the implementation details. So to make everything more concrete, from now on, I'm just going to assume that we are working with a large language model. But in principle, everything that I'm going to talk about also applies if you're working with other types of foundation models. So to generate an action with a large language model, we do autoregressive sampling, one token after another, until we sample a special end of sequence token. And this way of generating actions is extremely flexible because in principle, you can represent any action you can imagine with a sequence of tokens. So we are not really restricted to any predefined action space. And that turns out to be very useful in cybersecurity, where we very often have to tailor the action to a particular event, to a particular incident, or to a particular system. And this kind of sampling allows us to do precisely that. Now, once we have generated the actions, we then evaluate them through look-ahead predictions. And this is also an iterative procedure where we start out by generating the first action, like I just mentioned. Then we append that action to our prompt, and we predict the outcome of the action. And I denote that outcome with S1 here. Then we append S1 to the prompt, and we generate the next action, the potential future action, and then we predict the outcome of that action, and we continue doing this until we reach a desired look-ahead depth. And then we simply pick the action that, according to our look-ahead predictions, leads to the best outcome. Now, of course, the potential concern here is that while the predictions in many cases can be very useful, we don't really have any guarantee that those predictions will actually be correct. So in particular, the model could hallucinate and make up predictions. And that's precisely why we have this final step in our framework where we measure the consistency of the predictions. So the intuition here is that if the model really knows about the best action to take, and you query it many times with the same input, you will get roughly the same answer every time. It will differ a little bit in how it phrases it, but it will be roughly the same action, the same concept. Whereas if the model really doesn't know what action we should take, it will just make something up. And in that case, if you query the model several times with the same input, you can get completely different outputs every time. So the model is inconsistent and may even contradict itself. And based on that simple principle, we then have the following decision rule, where if the consistency, which I denote here with lambda, is above a certain threshold gamma, then we simply pick the best action according to the predictions. But if the consistency is below the threshold, then we abstain and we revise the actions through in-context learning from feedback. And like I mentioned, the feedback can be collected in many ways. It could be that we ask a security expert for feedback, or that we do a lookup in a database, or as I advocate for, we could collect feedback by evaluating the action in a digital twin. But regardless of how you collect the feedback, once we have collected it, we add it to the context of the foundation model, and then we ask it to generate a new set of actions to basically revise the actions. So in summary, our framework consists of three main steps. First, we use the foundation model to generate candidate actions. Then we evaluate the candidate actions through look-ahead predictions. And then we measure the consistency of the predictions. And if the consistency is low, then we revise the actions through in-context learning from feedback. And in the next few slides, I'm going to give some theoretical justification for this architecture, and I'm going to motivate why we have these different components here. So in particular, I'm going to present two main results. The first one is that we can control the hallucination risk by tuning the consistency threshold. So formally, I'm defining a hallucination. I've said an action is hallucinated if it doesn't contribute anything towards the task that we're trying to complete. And it could even be counterproductive. And by having a very high consistency threshold, we can make the probability of such hallucinations arbitrarily small. But the expense of that is that we may be more dependent on external feedback. On the other hand, if you have a low consistency threshold, we increase the risk of hallucination, but we will be less dependent on external feedback. But regardless of how we tune the consistency threshold, the second result is that if we collect enough feedback, then eventually we will converge to a consistent action. So when it comes to hallucinations, we don't really have any mathematical theory that prescribes exactly when hallucinations occur and why they occur. We have a rough understanding of why it happens, but there's no real mathematical theory behind it. So for that reason, we base our analysis on empirical observations of the foundation model. And in particular, I assume here that we have a calibration dataset of hallucinated actions that maybe a human has labeled for us. And given that dataset, we can then look at the distribution of consistency values in the calibration dataset. And based on that distribution and accounting for the finite sample size, we can then tune the consistency threshold to achieve a desired hallucination risk kappa. So the practical implication of this proposition is that we can adapt our framework to different security tasks. So in some tasks, like autonomous incident response, you may have very high requirements on hallucination risk, that they must be very low. And in that case, we use a high threshold. But in other security tasks, we're using it more as a decision support. Then you may be fine with some hallucinations, and then you can have a lower consistency threshold. And the proof of this proposition follows from quite standard techniques in conformal prediction theory. But regardless of how we configured the threshold, the second result states that eventually, if we collect enough feedback, then we will converge to an action that is consistent and satisfies the consistency criterion. And this result relies on two main assumptions. The first assumption is that we can view in-context learning sort of as a form of Bayesian learning. Of course, when we update the context of a foundation model, and we are not doing any Bayesian update. We are just changing the input to a neural network. However, there has been a lot of empirical studies showing that if you change the input to the foundation model, the output distribution of the network, so the softmax in the end, is roughly aligned with the posterior distribution in many cases. So it seems that the foundation model is doing some kind of approximate Bayesian updating internally when you change the context. And if we make that assumption, and we also assume that the feedback that we collect is banded feedback, so we get feedback in terms of our reward, in that case, we can show that in-context learning in our framework is equivalent to a form of Thompson sampling. And that means that we can invoke regret bounds for Thompson sampling, which are sublinear. And that, of course, means that if you collect an infinite amount of feedback, then eventually we will converge to an optimal action, and that action, by definition, will be consistent in our framework. So we have a few more theoretical results in our paper if you're interested, but those are, that I would say, the most practical results, the main results. So I will skip the other results in this presentation and move on to the experimental evaluation. And to evaluate our framework experimentally, we apply it to an incident response use case that involves a network system which consists of a set of interconnected components, some of which may be compromised by an attacker. And the problem here is to design a response strategy that uses measurements from the system to prescribe actions for responding to the attack. And when we are designing these actions, the goal is to mitigate the incident as quickly as possible, as illustrated by the following figure. So here on the x-axis you have time, and on the y-axis you have system performance and security. And at some unknown point in time, indicated by the left dotted line, an attack event may occur. And when that happens, we want the response strategy to quickly prescribe a sequence of actions for recovering the system to normal performance again, as quickly as possible. Unfortunately, designing such a strategy is challenging for many reasons. And one of the main challenges is partial observability. So when we are selecting the response actions, we do not have a complete picture of the incident, but rather we typically only have partial indicators of compromise, such as security alerts and logs. And we have to be able to make decisions based on that partial information. The second major challenge is that the action space is extremely large and unstructured. So essentially, any configuration you can make to your system is a form of a response. You can change the network topology, you can install new software on your servers, you can shut down some components of your system, etc. So it's a very, very large and unstructured action space. And the third challenge is that the response is time sensitive. And the best example of this is a ransomware attack, where a delay of just a couple of minutes in initiating the response can allow the malware to encrypt your system and then spread laterally across your network. So that's why automation is really desirable here, to have a quicker response. Now, the way that these challenges are managed currently in industry is through so-called security operations centers, where you have human operators that sift through security alerts and try to analyze them. And then in case there's a potential incident, they also try to respond. And while this approach can be very effective, it is very expensive. And currently we have a global shortage of more than 4 million of these experts. So there's a very clear and very pressing need for new systems that can automate some of these workloads and reduce the load on the security experts. And we have developed precisely such a system, which is based on the planning framework that I just described in the previous slides. But in addition to that framework, we also combine it with two additional components here, namely fine-tuning and information retrieval. So the purpose of fine-tuning is simply to align the foundation model to the objectives of incident response. And we do that by training it on a small data set of example incidents and response actions. So this step is not strictly necessary, but it can improve performance. It can improve the quality of the actions that are generated by the foundation model. And the second component, information retrieval, has a very simple motivation, and that is that if our foundation model is only trained on data, say, up until 2024, then it will have no way of knowing about vulnerabilities that were discovered later than that, say in 2025. So we want to make sure that before we generate actions with the foundation model, we retrieve all the relevant information that is required to make a good decision. And that's the purpose of the information retrieval step. So in our experiments, we fine-tune a lightweight version of the DeepSeek foundation model on a dataset of 68,000 incidents. And in the figure here, you can see the convergence of the training loss for two different learning rates. And what we can observe in this figure here is that both learning rates converge after around 8 hours or so, where the higher learning rate converges to a slightly lower loss value. And for the information retrieval, we use a very simple pipeline where before we initiate our system with details about some incident, like security alerts, we first run all of those alerts and information through a Python script that extracts certain keywords, like vulnerability identifiers or IP addresses, and then it uses those keywords to extract external information from public threat intelligence APIs. And then we simply append all of that information to the context of the foundation model. And for the experiments, we apply our system to 4 public datasets of incidents reported in the literature. So these datasets contain different types of security alerts and logs of an incident. And the task is to use those logs to generate a sequence of actions for recovering from the incident. And we then compare the generated sequence of actions with the ground truth, which is also available in these datasets. And in this bar plot here, you can see the distribution of attacker techniques or tactics in the evaluation datasets. Now for the baselines, we compare our system against the frontier models. So I did these experiments roughly 2 months ago, and at that time, these were the 3 frontier models. But now it has changed a little bit because OpenAI has a new model, ChatGPT 5. But I don't think that will actually change the results very much. And of course, the main difference between our system and the baselines is that our system is lightweight, and I run it on a very cheap GPU, a single GPU, a commodity GPU, whereas the foundation models require basically a whole data center to run, so they're much, much more expensive. And here is a summary of the main results. So we look at 3 different evaluation metrics here: recovery time, percentage of ineffective actions, and percentage of failed recoveries from the incident. So you want to keep all of those metrics as low as possible. And the performance of our system is shown in red bars. So what we can observe here is that our system outperforms the frontier models across all evaluation metrics and across all evaluation datasets. And if we compare the frontier models among each other, we can see that Gemini performs best on average, where the difference between DeepSeek and OpenAI is not really statistically significant. They are more or less the same in this case. And now the follow-up question, of course, what is it that drives the performance of our system? So why is it better than the frontier models? And to answer that question, we have done an ablation study where we have evaluated our system with and without each component. So in the top row here, you see the performance with and without information retrieval. In the second row, you see the performance with and without fine-tuning. And in the third row, you see the performance with and without look-ahead optimization. And in the fourth row, you see the performance with and without in-context learning. So what we can see here is that all of these components contribute positively to the performance. So if you remove any of these components, the performance drops a little bit. But exactly how much it drops varies quite a bit, where we can see, for example, that when we remove information retrieval, it's not a very big drop in performance. But when we remove fine-tuning, there's a very big difference. And I wouldn't say that these results are surprising, but they are still interesting because I've seen other studies where they have the opposite, where information retrieval is more important, but fine-tuning is not so important, for example. And I think that the reason why information retrieval is not so important in our case is simply because the incidents that we evaluated on, all of them are based on attacks that the foundation model already probably were aware about. So different attacker techniques that the foundation model already knew about, which means that it was not strictly necessary to collect external information. But it's still interesting that we got a small performance improvement anyway by collecting that information. So when it comes to the scalability of our system, there is, of course, a performance loss, or sorry, performance cost by doing the look-ahead optimization, because it means that we have to invoke the foundation model several times and do inference several times. However, the good news is that these inferences are scalable in the sense that they can be parallelized. So the more compute you have, the more GPUs you have, the faster you can do these look-ahead optimizations, as shown in the figure here. So in conclusion, it's very clear that foundation models will have a very big effect on cybersecurity. And exactly what effect they will have is still up for debate and research. My view is that they can enable this long-standing goal of autonomous security systems. And in this presentation, I have described a framework for realizing this vision. And I have shown that this framework outperforms frontier models, is significantly more lightweight than the frontier models and can run on commodity hardware, and it has stronger theoretical guarantees. So thank you very much for your attention, and feel free to contact me if you have any questions about this work. Thank you, and here are some references.